On the TPC pipelines interface, we provide several personalized analysis pipelines. Compared to the TPC modules mentioned earlier, the analysis on this page allows users to explore data integration, sample processing, and analysis modes in depth and personalized ways. TCGA has 4 series. PCAWG has 3 series. CCLE has 2 series. For each specific analysis pipeline interface, it can be simply divided into 3 parts. The left S1 panel is used for data and sample preprocessing. The middle S2 panel is used to prepare analysis data. The right S3 panel is used to execute analysis and download results, etc. Before introducing the specific usage of each process, we will combine the tutorial document to focus on introducing some key steps. Open the tutorial book webpage. Click to enter Chapter 11. As mentioned in the first section, we have integrated a large number of data types to facilitate users to perform arbitrary combinations of joint analysis. Taking TCGA as an example, there are 5 main types, which are molecular profile, tumor index, immune infiltration, pathway activity, phenotype data. According to the characteristics of the data types, they can be further divided into 23 subtypes. For example, at the molecular level, there are 7 omics types. And in the immune infiltration level, there are 7 calculation methods. For the core omics molecular data, in order to make full use of the UCSCXena platform data, we have prepared multiple datasets for each of 4 omics types. For example, for gene expression, we have 3 different datasets, which are TPM, FPKM, and norm_count. For methylation data, in addition to choosing 450K or 27K chips, users can further specify 1 or multiple CpG sites as the methylation level of genes. When conducting specific pipeline analysis, the above operations usually take place in the initial step S1.1. Using TCGA correlation analysis as the first example pattern, users can choose a type of omics to see if there are other optional datasets available. Below, the source of the currently selected dataset is provided. For user convenience in retrieval, we provide in the Help section TPC ID query interface. All integrated TPC ID data is provided and can be divided into 2 categories based on omics and non-omics. For certain types of IDs, relevant annotation information is also provided, such as gene chromosome information. In addition, in the phenotype data, custom metadata data type, users can upload 2 types of custom data. Similarly, using TCGA correlation analysis as an example, users can directly upload custom identifier data in step S1.4. Can download sample files to view format requirements. Here we have prepared an example file. The first column is the sample ID. The second and third columns are simulated user-defined data. Click the Upload button. Select our data to upload. Successful upload can be seen under Custom Metadata. Our data can be observed to have been successfully uploaded. For the second type, users can customize a molecular signature in step S1.5. In the dialog box that appears, users firstly need to edit the signature name. Here we modify the default name to signature_test. Then select the type of molecules it is composed of. Keep the default. Then we need to add the molecules one by one in the second step. Set coefficients for each molecule. Below it, the composition of the signature is displayed. Finally, in the third step, calculate the value of the above signature. After confirming its accuracy, it can be added to our integrated data. We can see that our data has been successfully added to custom metadata. The TPC analysis process was introduced in the second section. Advantages in sample processing. Based on the integrated datasets mentioned above, users can perform personalized sample selection and grouping operations. We also take TCGA correlation analysis as an example. Generally, sample selection needs to be performed in step S1.3. We provide two methods. The first method, quick filter, directly selects normal or primary tumor samples based on sample code types. Refer to the tutorial manual. We can browse the TCGA, the corresponding information of common sample coding types. The second method involves more complex filtering operations. In simple terms, users can filter suitable sample sets based on any one or multiple IDs of integrated data. In the dialog box generated by clicking, firstly, the user needs to choose one or multiple IDs as filtering conditions. As shown in the figure, the selected ID conditions will be renamed as condition_1, 2, 3, 4, and so on. Then, in the second step, we can observe each selected the conditions distribution. It is worth noting that the default common clinical phenotypes are used as filtering conditions. The third step starts the actual filtering operation. Users need to select one or more IDs from the second step and set the corresponding filtering conditions. For discrete variables, such as gender, users can set to retain or delete certain types of samples. The plus sign indicates retention. The minus sign indicates deletion. The above operation retained all female gender samples. For numerical variables, we can set directional thresholds to filter samples within a certain range, where sign is used to set absolute thresholds. In the first operation, we filtered samples above 60 years old. % and % are used to set percentile thresholds. As in the above operation, we filtered sample types above the 50th percentile of age. If multiple conditions are set, the filtering operations will be executed in sequence. Text prompt at the bottom. The current reserved samples. If the user sets two filtering methods simultaneously, the intersecting results of both filters will be taken. In some analysis pipelines, sample grouping is required. Using TCGA comparison analysis as an example. Step S2.1 can perform binary grouping based on the S1 sample selection. First, the user can select any ID from the integrated data as the grouping condition of interest. Then observe its distribution. For convenience of subsequent operations. For discrete variables, such as the encoding type here, display the frequency distribution of its categories. Then, it is necessary to designate one or more categories for each group. And modify the group names. For numerical variables, observe their percentile distribution. Then, set threshold ranges for each group. By default, it is set according to percentiles. If cancelled, it will be set based on the actual values of the selected ID. The interval for group 1 is left closed and right open, including the minimum value on the left, but not including the maximum value on the right. The interval for group 2 is closed on both sides, including the extreme values on both sides. It is worth noting that the ranges of the two groups may not cover all samples, but there should be no duplicated sample data. Finally, users can also change the order of factors between groups. After clicking the button, the current grouping results will be displayed in the text below. Based on the above introduction, we will demonstrate the operations of the TCGA pipeline with specific examples. In the first mode of TCGA correlation analysis, users can calculate the correlation of any two IDs in a specific tumor type. Step S1.1 can modify the omics dataset. Here, keep the default settings. S1.2 can select a specific tumor type. We choose CHOL cholangiocarcinoma data. In the S1.3 sample selection step, we use the quick filter control to select primary tumor samples. Steps S1.4 and S1.5 are used to upload custom data. Skip if not needed. Then in S2.1 we click the button to cache. In S2.2 we select monocyte from CyberSort as the predicted result of immune infiltration. Click the button to cache the data as the y-axis. Then in step S3.1 modify the method of calculating correlation. In step S3.2 modify the visualization parameters. Click other options to bring up more settings for visualization parameters. For example, we can change the title to TCGA-CHOL. Click the Run button to perform the analysis and present the visualization results. In step S3.3, the three buttons from left to right are used for downloading visualization results, raw data tables, analysis result tables. In the first button, next to the controls to adjust the length, width, and format of the image. In the second mode of the correlation analysis pipeline, users can calculate the pan-cancer correlation of two IDs. First, in step S1.1 we select norm_count as the source of gene expression data. Then in step S1.2 keep the default selection of all TCGA types. In step S1.3, use quick filter to filter all samples except normal. Then in step S2.1 choose HDC1 as the x-axis. Click the button to cache. In step S2.2 choose APOE gene expression as the y-axis. Click the button to cache. In step S3.1, for demonstration purposes, we change the correlation method to Pearson. Then click the Run, Calculate button to perform pan-cancer analysis. Then in step S3.2 adjust the visualization parameters. Finally, click the Run, Visualize button to present the visualization results. In the third mode of the correlation analysis pipelines, users can perform batch screen analysis based on specific tumor type to find results significantly correlated with a certain ID. In step S1, we selected primary tumor samples of CHOL tumor type. Then the user needs to select multiple IDIDs in step S2.1 as candidate filtering data. There are three ways to choose. 1. Select each from all IDs of the corresponding data type. 2. Select all IDIDs under this data type. For gene-related omics data, due to the abundance of molecules, users can select all genes under a specific pathway gene set. Three. Users can upload ID files that match the data type and can view the format requirements by downloading the example file. Here, we choose the second method to select hallmark genes related to apoptosis. Click the button to cache. Since we have performed similar analysis operations earlier, we can directly load here. If not, you need to wait patiently for some time. In step S2.2, we chose the monocyte of the CyberSort algorithm as the object for calculating immune infiltration prediction results. Then, in step S3.1, keep the default analysis parameters and click the button for batch analysis. Here, we directly use tables to display the analysis results. In step S3.2, Users can download raw data and analysis result data for local analysis and viewing. In the first mode of the comparative analysis pipeline, users can perform binary grouping for specific tumor type, and then compare group differences for an ID. First, in step S1.2, select the BRCA tumor type. And then in step S2.1, group according to its clinical phenotype code. Click the Observe button to observe the frequency distribution. Then, Group 1 selects TP and modifies it to primary. Group 2 selects TM and modifies it to metastatic. Click the Group button to group. Then in step S2.2, select POSTN gene expression for comparison. Click the Query button to cache the data. Then in step S3.1, select the comparison method. Here, we keep the default selection. And S3.2 can modify the visualization parameters. Here we modified the y-axis title. Click the Run button to perform analysis and visualization. In the second mode, users can compare group differences based on pan-cancer tumor types. In step S1.2, we keep the default selection of all TCGA tumor types. Then in step S1.3, first, select all primary tumor types based on quick filter. Then filter samples through the exact filter, selecting samples older than 60 years old. Next, in step S2.1, we group based on the gene. Mutation status of PTN. Here we need to cancel grouping by quantile. As group 1 is left closed, right open, with its interval set as 0, 1, representing the wild type. Then modify the group name. Group 2 interval is left closed, right closed. Set as left closed, right closed. And similarly modify the group name. Click the Group button to group. Then in step S2.2, select a tumor stemness score. As the data for comparison. Click the button to cache. Then for demonstration purposes, select the t-test as the analysis method. Click the Run, Calculate button to perform pan-cancer analysis. Then in step S3.2, modify the visualization parameters. Here we modify the title of the x-axis. Click Run, Visualize, to visualize. In the third mode of the TCGA comparative analysis process, users can perform binary grouping for specific tumor type and screen for significantly different ID between groups. First, in step S1.2, select the BRCA tumor type. Then, in step S2.1, group based on clinical phenotype code. Click Observe to observe category frequency. Then select TP for Group 1. And modify the group name. Select TM for Group 2. And similarly modify the group name. Click the Group button to group. Then select all immune infiltration prediction results under the XCLL algorithm in S2.2. Click Query to cache. Then in step S3.1, keep the default Wilcoxon comparison algorithm. Click Run to perform batch analysis. In the first mode of the survival analysis pipeline, users can compare the survival differences of specific tumor type in binary groups based on an ID. In step S1.1, select DNA methylation data. Choose the 27K dataset. Then select the CG152063330 site as the methylation level of gene TP5-3. Then in step S1.2, select the BRCA tumor type. In the quick filter of step S1.3, select all samples except normal. Select OS survival time in step 2.1. Group according to the methylation level in step 2.2. Based on the median level of TP5-3 methylation. Perform grouping. Then select log rank test in step 3.1. And modify the relevant visualization parameters. Click Run to execute the analysis and visualize the results. It is worth noting that, for continuous grouping variables, you can switch to using initial original data. This will automatically select the most significant grouping threshold for survival analysis. And reanalyze and visualize the results. In the second mode of the survival analysis pipeline, users can assign an ID to the pan-cancer tumor type and perform survival comparison in two groups. Keep the default selection of all TCGA tumor types in step 1.2. Then select primary tumor type through the quick filter in step 1.3. Select primary tumor type. Then in step 1.5, customize a molecular signature. After setting, you can see it in custom metadata. We observe that the signature we set has been successfully included. Then in step 2.1, select PFI survival time. In step 2.2, divide into two groups based on the lowest and highest 10% of signature values. Then in step 3.1, select univariate Cox regression. Modify the relevant visualization parameters. After confirming the above operations, click Run, execute the analysis, and visualize the results. We can also use initial data to perform group analysis based on the best threshold. In the third mode of the TCGA survival analysis pipeline, users can perform group comparisons of survival differences based on multiple for specific tumor types. In step 1.2, select the BRCA tumor type. Then, in step 1.3, select all samples except normal samples. Then in step 2.1, select OS survival time. In step 2.2, select all hallmark pathway activity data. Then group them based on each of their median levels. The results show group has already been performed based on all 50 IDs. Finally, in step 3.1, execute batch log rank test survival analysis and obtain the relevant analysis results. The basic analysis pipelines of the three series mentioned above are implemented in the PCAWG and CCLE datasets. No examples will be given here, but you can refer to our tutorial book for complete usage assistance. In the most recent update, TCGA cross-omics analysis has been added, which can simultaneously analyze gene or pathway pan-cancer features in multiple omics. Taking gene cross-omics analysis as an example. S1.1 modifies the dataset only for the sample selection step in S1.3, while in the subsequent cross-omics analysis, we have selected a fixed dataset for each omics, which will not be affected by the S1.1 step. S1.1 and S1.3 steps are used to select pan-cancer tumor types and sample filtering operations. The method is similar to the previous analysis process, so we won't go into detail here. Then the user needs to select a gene in the S2.1 step. Then load its gene expression, mutation, and CNV data in the S2.2 step to save time for subsequent analysis. S2.3 and S2.4 are used to select and load multiple transcripts related to the gene, as well as methylation site data. Analyze and visualize in the S3 step. Users can click the button in the upper right corner to get the meaning of each column in the visualization. They can also download the images to their local device to get a clearer presentation. We have automatically set the optimal length and width based on the content of the visualization. Users generally do not need to make additional settings.